All right. Yeah, I'm representing Professor Ning from Sichuan University to make the presentation. Because of visa issue, the authors of this paper cannot come here. And I'm not one of the author of this paper, so I may not be able to answer all the questions, but I will still try my best to make this presentation go well. Okay, so hello everyone. The paper I want to present today is Adaptive Fair Representation Learning for Personalized Fairness in Recommendation via Information Alignment. In the era of exponential information growth, recommendation systems play a critical role in alleviating the problem of information overloading. Despite the great success of recommender systems, existing studies have shown that machine learning based recommendation models often suffer from unfair recommendations. The potential cause of unfair recommendation results is the bias associated with the sensitive attributes in training data. As an example of the job recommendation in this figure, the training data may contain social bias. For example, when there's an open high-paying software engineer position, if there are two candidates with similar qualifications, one man and one woman, the model might recommend this position to the man candidate and not the woman candidate. This is unfair to the woman candidate just because of the bias in the system. In the recent years, fairness is becoming one of the most popular topics. Who should be treated fairly? Recommendation systems are complex systems involving multiple different kinds of people, and which include the users, items, and platforms. Existing research typically focuses on user-side fairness and item-side fairness. Among them, user-side fairness attracts special attention due to its significance to the importance of the user experience. In our paper, we only focus on the user-side fairness. A range of approaches have been proposed for user-side fair recommendation. The common idea of them is to filter out the information of user-sensitive attributes from the learned fair user embedding, so that the recommendation can be made independently of the sensitive attributes. However, the traditional approaches ignore personalized fairness requirements. They often assume that all users share the common sensitive attributes and consider the user fairness requirements represented by a collection of user sensitive attributes as hyperparameter specified in advance, which limits the model to serve only one fairness requirement. In the real world, however, it is the fact that different users different users are sensitive to different attributes and have personalized fairness requirements. For example, some users may want the recommendation to be made for them without considering their age, while some other ones want the recommendation to be made without gender bias. Recently, a few methods have been proposed for personalized fairness in recommendation. For example, Li and Wu proposed to train a filter for each possible combination of sensitive attributes. Krieger proposed a disentangled representation learning that separates representations into sensitive and non-sensitive subspaces. However, the problem of personalized fairness in recommendation is still far from being well solved, partly due to two challenges. First, unacceptable training costs caused by exponential combination of attributes. Essentially, most existing methods for personalized fairness still treat a fairness requirement as a hyperparameter, which make them have to train and store a model for each combination of attributes in a brute force way. The second The second is compromise on recommendation accuracy. In order to completely erase the sensitive attribute from the fair embedding, the existing approaches also remove information that overlaps with non-sensitive attributes. This inevitably causes the loss of the discrimination information of the non-sensitive attributes and result in a suboptimal trade-off between accuracy and fairness. So in this paper, to address the above challenges, we proposed a novel fair model called Adaptive Fair Recommendation Learning, shortened as AFRL, for personalized fairness recommendation. To reduce huge training costs incurred by the exposure of attributes combinations, AFRL treats a user fairness requirement as input rather than a hyperparameter. The generation of fair embeddings is dynamically controlled by the fairness requirement. To strike a better trade-off between the fairness and the accuracy, AFRL conducts a novel information alignment to exactly preserve discriminative information of non-sensitive attributes. And our proposed AFRL incorporates a debiased collaborative embeddings into the fair embedding to capture attribute-independent collaborative signals without loss of fairness. This picture gives an overview of the architecture of our AFRL. The input of AFRL are the original user embedding U and the personalized fairness requirement SU, and then produce the fair embedding U star. So we can see that AFRL consists of two modules. The first one is the information alignment modular, and the second one is the information aggregation modular. So let me introduce these two modular. The information alignment modular is responsible for learning attribute-specific embedding for each attribute and a debiased collaborative embedding from the original user embedding U. The bottom red box are attribute-specific embedding, the UI. Here we ensure the precise alignment of information between the embeddings and their respective attributes. Information alignment refers to preserving and only preserving the discriminative information related to the attribute within the corresponding attribute-specific embeddings. The top red box is debiased collaborative embedding ZU0. It encodes the debiased collaborative signals, which are the collaborative signals independent of the user attributes. Once the attribute-specific embeddings and the biased collaborative embeddings are produced, information aggregation modular will combine the UI and the ZU0 based on the personalized fairness requirement SU to produce the final fair embedding U star. Next, we will provide a detailed introduction to the implementation of the model. Information alignment modular is responsible for learning attribute-specific embeddings for each attribute and a debiased collaborative embeddings from the original user embedding. Hold on, this is the previous one. The attribute-specific embedding ZUI of the IS attribute of the user U is extracted by the attribute encoder EI from the original user embedding. Since EI is shared by all users, the output of EI can be represented by a stochastic variable ZI. Our objective is to make EI achieve information alignment between ZI and AI, where AI is a user attribute. To achieve information alignment in the light of the information bottleneck principle, the optimization objective of EI is to maximize the mutual information between ZI and AI and simultaneously minimize it between ZI and U. The image here illustrates the insight of the attribute-specific embedding learning for information alignment defined by the equation. The circle area represents the information content of the corresponding variables. We can see that the amount of the information encoded in Zi can be regularized by beta. The ideal moment is shown in the figure C. Zi covers the information of AI and Zi and only covers the information of AI. In this way, we can avoid the loss of the discriminative information of non-sensitive attributes and achieve a better trade-off between accuracy and fairness. The original unfair user embedding U provided by the given unfair recommendation models has encoded the collaborative signals biased to the user attributes. Information alignment module employs a debiased collaborative signal encoder F to generate the debiased collaborative embedding ZU0 to capture from U the collaborative signals is independent of user attributes. For this purpose, we optimize F with two objectives. The first is minimizing the discriminability of ZU0 to user attribute for fairness, and number two, maximizing the information of U encoded in ZU0 to preserve the collaborative signals as much as possible for recommendation accuracy. To achieve objective one, we use adversarial training, and for the objective two, we minimize the reconstruction loss. After obtaining the attribute-specific embedding, the UI and the debiased collaborative embedding, ZU0, the information aggregation module, which is implemented as an MLP, combines these embeddings based on the personalized fairness requirement SU to produce the final fair embedding U star as follow. To ensure the U star to be compatible with the original recommendation model, the MLP will be adjusted with respect to the supervision offered by R. We also conduct theoretical analysis of the implemented method to ensure their effectiveness. The first is convergence analysis. We analyze the convergence of the bi-level optimization, which is tractable approximation to realize the information alignment. The second is informativeness analysis. We show that AFRL completely extracts the information in a non-sensitive attribute into the fair embedding. So in the experiments, we primarily address four questions. The first is how does the model compare to the state-of-the-art models? And the second is how AFRL make trade-off between fairness and accuracy. And the third one is how do the attribute-specific embedding and the biased collaborative embedding contribute to the performance. And the last one is the hyperparameter. So the baseline we used have two categories. One is the models achieve the personalized fairness, and the third one is for the recommendation. So this table show the performance of AFRL and the baseline models on movie learns 1 million. So we can see that for the accuracy, most of the cases AFRL outperforms the baseline fair models, which indicates the AFRL can achieve less accuracy loss. We also did some other experiments for the trade-off between the accuracy and the fairness, and also the ablation study, but we don't have enough time to introduce them in detail. So yeah, if you are interested, you can we can talk offline and also like read the paper. So in conclusion, in this paper, we propose a novel model called adaptive fairness recommendation learning for personalized fairness in recommendation. Yeah, thank you for your attention.
Thank you very much.